we are going to be looking at electricity. So I thought what we would start with is a very quick recap of the electricity, the most important concepts, and then we're going to go straight into the questions. So very quickly, starting off with the whole concept of resistance. Resistance is when there is opposition to the flow of charge. So that sounds very fancy. What does it mean? Essentially, it just means that I've got these charge carriers in my wires that are moving. And when there is resistance, it means there is some difficulty. They're having to transfer energy to pass through the wire. So very simple, we all like analogies. It's like you walking through a classroom that's filled with air, that's quite easy. But if someone fills that classroom with water, it's going to be quite difficult. So there's a lot more resistance to you being able to walk. So resistance in terms of electrical current and electrical circuits, there are 4 factors that affect resistance. The first one is length. If you increase the length of a resistor, you increase the resistance. Then there is diameter or thickness. If you increase the diameter, this is the one that works the other way, you decrease the resistance. Then we get temperature, which is an important one when we're going to look now at Ohm's law. If I increase the temperature, I increase the resistance. And lastly is the type of material. So when we're looking at the type of material, very simply, we know that our electrical wires, or hopefully you should have some concept that the electrical wiring in your home is made of copper. And that is because copper has a lower resistance than something like nichrome. So that what it is made of also affects the resistance. So resistance, as I've already done here, is measured, has a symbol R. As James mentioned, we're going to talk about internal resistance later, where that will be a lowercase r. Don't confuse that with radius from what you've just done with gravitation. The unit of resistance is the ohm, which is your omega, Greek omega symbol. So now when we're looking at electrical circuits and we've got to make a decision about how do I find the resistance, what else is happening in a circuit, the other important concepts are current. Okay, current is how quickly my charges are flowing through my circuit. So that is the rate of flow of charge. Current has a symbol I. You'll probably remember from previously you did I is Q over T, where you're calculating from charge and time what is the current. The unit of current is the ampere, which has as a symbol a capital A. So current is how quickly charges pass through my wire. Now, because it's how quickly charges pass a point, we need a device that allows us to measure how quickly those charges pass the point. So we have a measuring device in a circuit known as an ammeter, and that is the symbol for an ammeter. And an ammeter is placed in series in a circuit. So we're going to look just now also at the series and parallel part, but I need to place an ammeter in series. So I'm going to draw a circuit for you now with all of these in. Then the next concept that we talk about is potential difference. Some people sort of get lazy and they talk about voltage. The symbol for potential difference is V. The unit of potential difference is the volt, which has exactly the same symbol, which is V. Now, potential difference, again, you sort of started, when you first started with electricity, you used these definitions. Potential difference is defined as the work done by those charges as they move between 2 points. So it's clearly in the word, it talks about potential difference. So when I need to know what is potential difference, it's got to be between 2 points in my circuit. You don't have potential at a point. We always talk about potential difference between 2 points. So when we're looking at a circuit and how can I measure potential difference in a circuit, we use something known as a voltmeter. And the symbol for a voltmeter looks like that. And because I needed to measure between 2 points, I place a voltmeter in parallel in a circuit. So let's look at a very simple circuit. So in a circuit, I'm going to have a battery or a cell. I'm just going to draw one cell here. Remember, for when we get to something later on, that's a positive and that is a negative. I'm going to place in series in my circuit an ammeter. So what do I mean in series? It means it goes one after the other. Then I'm going to place circuit symbol for a resistor and close my circuit. I'm going to add a little switch here. There's a switch S. And then if I want to measure the potential difference across the resistor, I'm going to put a voltmeter between 2 points. So that voltmeter at the moment is connected in parallel with the resistor. And the ammeter is connected in series with the resistor. Now, just because we're going to now talk a little bit about resistance and calculating resistance in circuits, I'm just going to add, while we're here with the voltmeter and the ammeter, note that because an ammeter is placed in series, when someone makes an ammeter, they need to make sure that it has a very low resistance. Okay, so when someone builds an ammeter, knowing it's got to be in series, they've got to create an ammeter that has a very low resistance. So you'll see in a lot of questions that you get, they'll say the resistance of the ammeter is negligible, which means you can ignore it, which is what we need to do so that we can actually not have to worry about it. In the same way that we have to have a very low resistance for ammeters, because we're placing voltmeters in parallel, we need to ensure that when we build a voltmeter, it has a very high resistance. And again, you'll see in a lot of the questions, if someone has worded the questions properly and correctly, they are going to state the resistance of the voltmeter is very high, which then means you can ignore it in your circuit. And in fact, we are going to get to a question where someone by mistake puts a voltmeter, an ammeter in parallel, which will cause a problem in a circuit. So those are sort of the main sort of parts that we deal with. So quick recap, we've got R, we've got I, and we've got V. So now when we're looking at the first sort of thing that you looked at probably when you started grade 11, comparing it to what you did in grade 10, is we do something known as Ohm's law. And Ohm's law is where we're looking at, for a particular resistor, what is the relationship? So for some sort of resistor, what is the relationship between V and I? So what is, again, let's draw a little circuit that we can use. So here's my ammeter, here's my resistor, and here's my voltmeter. What I'm looking at is looking at the current that flows through the resistor. So that would be the reading on this ammeter, and that would give me my I. And what is the potential difference across the resistor? And that is my V. And when we look at this relationship, what Ohm found is that for certain types of resistors, which we're going to call them ohmic, that there was the current was directly proportional to the V, or you can say the V is directly proportional to the current. So what does that mean? So a reminder about this concept of direct proportion. So you guys are all now in the second year of your sort of FET maths. You are starting to see more and more in science, your maths is becoming incredibly important. So you are expected to be able to take the concepts of direct proportion and inverse proportion and bring them into your physics. So you've done Newton's laws today, and you learn about Newton's second law, where you talk about how the net force is directly proportional to your acceleration, sorry, is directly proportional to your net force. what does that mean in terms of maths and in terms of physics? It means that I'm able to actually draw a graph of the potential difference across this resistor. So looking at the circuit that I've got here and the current through the resistor, and I should get, if they're directly proportional, I'm going to get a straight line through the origin. So direct proportion means that you will end up with a straight line graph. That's the top there. Okay. And it will definitely go through 0, 0. Okay. So remember, what does that mean in terms of maths and in terms of what you learn in maths? It means you've drawn y equals mx. There won't be a plus c because remember your y-intercept is in fact 0. So if I look at this v and this I, and I look at finding the gradient of this line. So remember, again, we're now doing a little bit of maths. Gradient y2 minus y1 over x2 minus x1. So if I look at this particular graph, what I'm going to find is that my gradient is going to be a change in a v over a change in an I. And if we go back to what did Ohm define as this v over I, that is going to give me my resistance. So the gradient here of this graph is going to be R, the value of the resistance of my resistor in the circuit that I have here. Okay, now this is only true if one condition is kept constant. And this is where this concept of these resistors obeying this direct proportion rule becomes sort of important in terms of what I do in a circuit. So when we look at Ohm's law doesn't just tell me that the potential difference is directly proportional to the current, or that the current is directly proportional to the potential difference. It also states that it must be at constant temperature. And I go back to what I started the lesson with. Remember that temperature has an effect on resistance. And that is why when we look at Ohm's law, we have to keep the temperature constant of that resistor. So in an actual experiment you would do in class, you wouldn't let the current run for very long, because the longer you let it run, the hotter your resistor gets. So you actually take a reading and you switch off the current. So if I plot this graph, it allows me to get a straight line through the origin. And if I find the gradient of the V versus I graph, I've actually found the resistance. So that means, just to give you an example of possible questions, if someone gives me a V versus I graph, and they give me two graphs, and let's say there's A and there's B, and they ask me to give some relationship between the resistance of A and the resistance of B, all I need to look at is the gradient of my line. And since my graph is V versus I know that my gradient is R, and therefore that means that since the gradient of A is greater than the gradient of B, the resistance of A is bigger than the resistance of B. So that is one way of representing Ohm's law in a graph. Unfortunately, you also, is everyone okay with that? Sorry, you guys must interrupt me if I'm going too quickly or there's something that doesn't make sense. Anyone got any questions so far? All good. So unfortunately, there are two ways of doing the Ohm's law experiment. And the second way of doing the Ohm's law experiment is where, in fact, you end up plotting a graph of I versus V, not V versus I. You still get a straight line because remember we said potential difference is directly proportional to current, or current is directly proportional to potential difference. But now we've got to be very careful. So you've got to look, what are the things on your axes? So now gradient, remember, y2 minus y1 over x2 minus x1. So now I'm doing a change in I over a change in V. So Ohm's law says to me R is V over I. Therefore, what does I over V give me? And that means that I over V is 1 over R. So you've got to be very careful at looking what was plotted on the axes. If it's V versus I, the gradient is the resistance. If it's I versus V, the gradient is 1 over R. Which means if I again go and show this example I gave you just now of IABV, and I have resistor A and resistor B, and I ask you again, what is the relationship between A and B? If I look at the gradient of A is greater than the gradient of B, but what is the gradient? It means that 1 over R of A is greater than 1 over R of B, which means, in fact, the one that has the greater is going to be the one that has the lower gradient. So you've just got to be very careful. And we actually is one of the questions that we're going to look at just now that has one of them where you've plotted it the other way around. Okay. Everyone okay with my, okay, yes, hands up. Chris.
Ma'am, sorry, aren't you able to manipulate your second form of Ohm's law to get back to the original of R equals V over I? Because if you flip the R and the 1, you still get R over 1 and V over I.
Yes, you do, Chris, but what you've got to be careful of is if someone asks you to find the gradient of the graph and you've got to plot I versus V, Chris, the answer you get, you're going to have to flip afterwards. So when you have, if you were plotting a graph and you ended up finding the gradient and you got an answer of 2 as your gradient, your last step is you're going to have to say, okay, but the gradient for this particular graph is 1 over R. So it means it's actually a half, which means that your resistance, Chris, will be 0.5.
Okay, thank you, ma'am.
Yeah,
I appreciate
but you're right.
Confused because, as you said, like it makes a big difference, especially if you put it in as a fraction.
Yes,
so.
And that's the problem, is that unfortunately it's the way you there are 2 ways of doing the experiment, to be honest with you. One of the ways which to just sort of show you circuit wise, in fact, I'll tell you what, let's look at the question, because I think if we look at the question, then maybe let me just find, I know I haven't done anything yet about non-ohmic. So just give me a second. I just want to now going out of my order of what I'm doing things, but it's all good. Here we go. Let's look at question, everybody. So sorry, the DBE guys, you're going to notice that everything I have on the screen, you're 1 question behind. So if you've got the DBE revision notes and questions, yours will be 6.3 and the IEB will be 7.3. So let's look here at what this person has done in this investigation. So a learner investigates the relationship between the current and the potential difference. So the first thing you guys have got to be aware of is, you know, science teachers and science examiners, they love testing, do you know independent and dependent variables? And a lot of the times kids get worked up and they say, oh, I don't know what the independent is and what the dependent is. Invariably, it's given in the first sentence of the question. So remember your independent variable, I always call it the I change it. So it's the one that you change. I change something. And then the dependent variable, it's almost like what it is. It depends on the independent variable. So the independent is the one you're going to change every time, and the dependent is the one that you measure. So this is the one you change, and the dependent is the one that you measure. So they're saying here investigates the relationship between current and potential difference in across a resistor. So we know somehow one of them, current, is going to be my independent or dependent, and potential difference is going to be the other. So if I look here and I look at the apparatus that the student uses, so let's go and look what they've got. They've got a battery, they've got a switch, they've got an ammeter, so they're able to measure the current. So we know that's going to measure our current. They've got a resistor, and they've got a voltmeter across the resistor, so that's going to measure our V. And now they've got this other funny device on the side, a resistor with an arrow through. What is that? So a reminder from your circuit diagrams, that is known as a rheostat. So what is a rheostat? A rheostat is a variable resistor. Now, what is a variable resistor? If everyone can, a variable resistor is like a dimmer switch. So for example, I'm just going to do you an example. I'm going to turn my light down and up. So you'll notice my light, it goes dimmer. I don't know if you can take note. And then the light gets brighter. That is me turning a dial, and it's like a variable resistor. I'm changing the amount of resistance. Now, what is the purpose of the rheostat in this circuit? Well, what it is doing is it's going to, if I make this bigger, and I know I'm jumping the gun here a little bit, we haven't done any circuits, but if I increase the value of this resistance here, this rheostat, I'm going to change the current. So what that means is that my current is the thing that I am changing. I won't state that resistance is my independent variable. Because I'm changing this rheostat, I'm going to make it R1. Let's make it X. Sorry, it is X. I'm being silly. I'm going to increase the value of Rx. And what will happen is it means I'm going to change my I. And then once I change the I, I'm going to measure the V. And that's why in this experiment, the I, the current, is the independent variable, which shows you how naughty the person is who drew this table, because in this table, the person has incorrectly placed the ammeter reading in the second column. When we look at drawing up columns correctly, you always put your independent variable in your first column and your dependent variable in the second column. So this here, is incorrectly drawn, and then it leads to children making a mistake because the kids learn, the teachers have said to them, independent first column, dependent second column. So you would look at this table and think, okay, someone has correctly drawn this. But actually this version of the experiment where you're changing the resistance of something else and it therefore changes the current, that is where current is your independent variable and potential difference is your dependent. So here, if I was going to plot a graph from this here, it would work out like I wanted to. So this one, it's going to mean that I actually am changing my current. And remember, your independent is always on the X. Oh, sorry. And you measuring, so this is where your dependent goes, which means that if you had to plot these points, you would end up with, hopefully if it is following the rule, a straight line through the origin. Okay, so here, this experiment is where I is the independent variable, where I do get that the gradient here is going to give me my R. Okay, so if we look then at the rest of the question, which in the end they didn't ask you Write down the name of the physics law the learner is investigating. Anyone want to help me quickly? Quick answer, either talking or you, Storm.
Ohm's law, ma'am.
Well done, Storm. Thank you. So this is Ohm's law. Okay, what factor must keep constant during the experiment?
Temperature.
Well done. I didn't see who that was. Sorry, temperature. Names are moving up and down a bit. Formulate a suitable hypothesis. So now just to talk about this concept about hypothesis, okay? There are clear rules, and those of you you get eventually in grade 12, you're going to get like exam guidelines. So the DBE bring out an exam guideline document, which your teachers will share with you. The IEB have something called the subject assessment guidelines. And they state in there what is needed for a hypothesis for dependent and independent. So just to talk about a hypothesis, firstly, just in general, is that when you have a hypothesis, you must mention your two variables. So you must talk about your independent, it must be mentioned. You must talk about your dependent. And thank you, Retendo. Sorry, I didn't see it. You must mention the relationship. Okay, now the dependent depends on the independent. So we've said in this investigation that V was our dependent. And we said that I was our independent. So when you give your hypothesis, grade 11s, you've got to be very careful. You are not going to say as V increases, I increases. You have got to say as your independent, it's got to be your independent because that's the one you change, as your current increases. And then you mention your dependent, which is your potential difference. And in this case, let's go and check if I'm right. As the one goes up, as the current goes up, yes, the potential difference or the voltmeter reading. I suppose you could have stated the voltmeter reading. The potential difference increases. So there I've mentioned my variables, I've mentioned my dependent, I've measured independent, sorry, I've mentioned my dependent, and I've mentioned the relationship between them. As the one goes up, the other goes up. So when you give a hypothesis, please, in this case, they gave you a table, and that is why you can formulate your hypothesis from the table. Now they're asking in this investigation, is the potential difference the dependent or independent? It should be an E. So remember we said that in this investigation, it is the dependent. Okay, I'm just check. I seem to, yes.
Sorry, I would just like to ask, because with Ohm's law, you can either take potential difference or current as the independent.
Yes.
So in this case, could you also see it as not being a mistake where the voltmeter readings are given first because it's Ohm's law?
No, you know, what I'm going to do, I'm going to speak. Sorry, you know what? I can't. Is it Chris?
Yes, ma'am.
Sorry, you know, I just want. You do go to the top. I keep forgetting, of course. So, Chris, I'm going to show you an example where I would do an actual investigative question where V would be your independent. So, because unfortunately, this setup that's here, you are changing R to change I. And therefore, I is very clearly your independent variable. Okay, so you've got to be careful. In this one, it very much is. So Chris, if I wanted to do the other one where V is very definitely my independent, that would be, I'm just going to say, so experiment 1, I would do this. There we go. I'm just going to be very rough here. Sorry, my circuit, I suppose, must close. That would be experiment 1. I would put one cell and I would measure the current and the V. Experiment 2. Can you see how I'm changing V? I've added another cell. So this, Chris, is how you would do the second type. And then your third experiment, let's say you had 3 experiments, you'd add another cell. So if you were doing it in the lab and you changed the number of cells, then this one here, your V is your independent.
Oh, okay.
And
Thank
your
you.
I is your dependent. So can you see how in this one I changed the amount of volts? And
Yes.
and the other one the other one is, so having this rheostat here, Chris, made it that it was current I was changing.
Okay,
Okay.
thank you. I appreciate
Yeah.
it. Thanks.
No, all good. You must ask. And then they ask, write down the name and state the purpose of the piece of apparatus. You know, my problem with this is that some of these questions really are the wrong way around. They should have actually asked you number V before number 1V, because it's hard to work out, as Chris picked up, that why can I not say that V is the independent? Why can I not assume the person made the correct, that they put the right thing in the first column? So here, for me, this question should actually have come here so that you could have thought about, why is this there? Because even the first statement they gave you, that, you know, it's not necessarily clear that the current is the independent. So a better statement here as well would have been, investigates how the current in a resistor, so you know what I mean, how the current in a resistor affects sort of the potential difference. Then you would have clearly seen that current, because someone's saying, how does current change or affect potential difference? So even that first statement was a little bit sort of vague. So since we're busy with Ohm's law, I'm just going to go back and just talk quickly again about ohmic and non-ohmic, and then we're going to come back to that question that we didn't do now, 7.1. So we know now from Ohm's law, R is V over I. We also know from Ohm's law that for this to be true, I must be at a constant temperature. So if I'm now looking at, sorry, I must just go out here quickly. So if I look at my graph now, and I do, again, I'm just going to make life easy for us at the moment. And I'm going to plot V versus I. Okay, then that straight line, let's make that A. That means that for A, the resistance of A will follow Ohm's law. So what does it actually mean in reality? It means that that resistor at constant temperature will have a constant resistance value. So now if I have this resistor A, it is known as an ohmic resistor. So an ohmic resistor is one that obeys Ohm's law. It's one where the potential difference is directly proportional to the current at constant temperature. So what does a non-ohmic resistor look like, and how does a non-ohmic resistor change? Well, what happens with a non-ohmic resistor is that you find you don't get a straight line. And in fact, if you look at that graph, and I'm just going to show you, so let's make that B. So if I look at the resistance of B, V over I is not constant. Okay, and how do I know it's not constant? Because you guys are good, you know how to do your maths. If I had to take this and do the gradient, can you see how the oh my terrible drawing, sorry. Can you see how the gradient is getting steeper as I go, the current increases? And in fact, what's happening here is that as the current increases, the resistance of B is increasing. And you find that for most of these, and non-ohmic resistors, the resistance increases with an increase in current. So that would be non-ohmic. So you will not get a constant V over I. So if we go back, so let me just write here so that you can see it. So that is non-ohmic. Okay, V over I is not constant. So if we go back to the questions, and let's go up to question 7.1, I think it was. I've got your 7.1a. Okay, here we go. So for DBE, this will be 6.1. Let's just go back to my blue. Okay, the two graphs below show the relationship between current and potential difference for two conductors X and Y. So now they've plotted the current I in milliamps. Just be careful if you were actually going to read values. Remember the little m is milli, but I think you all are on top of it since you've been doing mechanics this morning. And then they've got resistor X and resistor Y. State Ohm's law in words. So that is that the current, remember, is directly proportional to the potential difference at constant temperature. Which one of the following conductors is ohmic? Okay, who's going to tell me quick? Who's going to answer? X or Y?
X, ma'am.
X, well done. So X is my ohmic resistor. And they want you to refer to the graph and give a reason. Well done, Rutendo, you quick. You know what happens is I seem to be, I'm just going to go everyone. I think that's why I'm not seeing, it seems to be defaulting to only one person's name. So if they ask you why, not why, sorry, that's terrible. It's like, why is it why? You're going to, when they say refer to the graph, you are then going to be talking about the, either you can talk about the gradient of the graph, and that the gradient, you could talk about the fact that the gradient is constant. And then I would always add in, what do you mean by the gradient is constant? That V over I is constant. Okay, or if you were doing for this particular graph, I over V. Okay, so this one was I over V, because if you look, Y is I. But you're looking at the fact that your V over I is a constant value, and that tells you that it's ohmic. If I look at Y, I want to talk about this a little bit, because some questions sometimes will be, what is happening to the resistance of Y as the potential difference increases? Someone want to venture a guess? What is happening to the resistance of Y as the V increases? Can someone tell me, is the resistance of Y increasing, or is the resistance of Y decreasing? Decreasing, I can, Letabo. Okay, anyone else? Rutendo, decreasing. Okay, Letabo and Rutendo, is that because you're seeing that the gradient is decreasing as you're going along? Which you correct, okay? And this is where it can be quite nasty, and these are the nasty ones. Yes, the gradient is decreasing, very correct, but be careful. If I look at this graph, the gradient is in fact, let's go and look here, the gradient is in fact I over V. And therefore, unfortunately, in this example, this gradient in this graph is 1 over R. So if 1 over R is decreasing, can you see that therefore R must be increasing? Please, you must tell me if this doesn't make sense, because then I'll actually give you numbers. Okay, if someone is unsure why, if 1 over R is decreasing, R is increasing. So for example, just to show you, because I think sometimes as teachers, we don't realize that numbers do sometimes, okay, pretend I'm going to go through that. So if I look at this 1 over R, and I'm going to go put in numbers. So let's make R get bigger. So if I take 1 over 2 and I compare that to 1 over 5, So R, which is the bottom number, has got bigger. But can you see that 1/2 is actually a half and 1/5 is 0.2? Can you see that as the R, which is the bottom number, gets bigger, 1/r is getting smaller? Does that make sense, Rutendo? Can you see that? Yeah, so unfortunately in this one, yes, you guys, you were spot on the grade, because I know, because we've been talking about gradient, so well done on that, that you knew to look at gradient and that the gradient is getting less, and it is. But unfortunately, this is the one where it's I versus V, and that means that the gradient is decreasing, which means 1/r is decreasing, which means in fact your resistance is increasing. So it is a nasty one. So I think there was one more that was 7.4. It's just, or 6.4. Let's just, yeah, I thought there was one more Ohm's law one. Oh, here we go. Okay, 7.4 and 6.4 for the DBE. Learners investigate the conducting ability of two metal wires P and Q made of the same material. They connect both wires in a circuit as shown below. The potential difference across the wires are increased and measured. The resulting current through these wires is measured. Wires are increased and measured. The resulting current through these wires is measured. Using the measurements, the learners obtained the following sketch graphs. So the first thing I want you guys to do with your questions is this should actually be wire P, not R. Okay, so just to change that to wire P on the graph. And now again, just to show you, if you look at the statement here, they said the potential difference was increased. That means that is what someone changed. So that is the independent. And that is why it is on the x-axis. And the resulting current was measured. And therefore it means that my current is my dependent. Okay, so if I look here, the current is on the y-axis and potential difference is on the x-axis. So now, if they have different gradients, what is that telling me is different? You can tell me what's different about the two wires if they've got different gradients.
The resistance, Mom.
Resistance. Everyone else okay? Everyone else happy with the fact that it's resistance? Sorry, I did something very silly there. Okay, so the one possible difference now, but now the resistance is different, but now they want me to talk about physical difference. Okay, so a physical difference means I have to say something that's different about them. So yes, very correct, the resistance is different. How can I have two wires and make their resistance different? Someone want to venture a guess? What can I change about the wires to make them different?
The thickness.
The thickness. Someone want to give me the other one?
Isn't it also the steepness of the gradient?
Yes, yeah, no, that's going to give it. How can I change the actual, when I make up the circuit, how can I make sure material of the wire, Priyanka, very good. The type of material, the type of good, and there's one more. What can I do? I can make it
Longer or shorter.
Tamara, yay, thank you. Good. So it's thickness, it's length, and it's type of material. So any of those would be possible things I can change to change the resistance in that circuit. Now they're asking which of P and Q is a better conductor. Okay, so now, what is a better conductor? So now we know that we like to use copper wire in our wires at home. Because why do we like to use copper wire? What is the reason we're using copper wire? because it has what property? It's got a lot of properties, sorry, that's very vague. But in terms of what we're doing at the moment, what is an important property that copper has compared to other? Well done, Priyanka. It's got low resistance. And that makes copper a better conductor. Okay, so to be a better conductor, so please, you need to keep track of this, that to be a better conductor, you must have a lower resistance. Okay, so we need to find which of these has the lower resistance. Okay, so again, unfortunately, what have they done? They've put I versus V. Okay, so if they've put my gradient then here, again, is I over V, which again is 1 over R. So which of these would have the lower resistance? Sorry, P or Q? Q, well done. Q, sorry, give me a second. Yeah. Resistance. Okay, so again, well done, Q. Why is it Q? Because the fact is that Q has the steeper gradient, okay, and therefore, if it's got the steeper gradient, it's got 1 over R is the biggest, which means R is the smallest. So very well done. So you would state, so what is, you've got to explain your answer. So let's just go along here. So you would state that it's Q, and you would say that the gradient is equal to 1 over R, okay? And therefore, and you're going to have stated that a better conductor has a lower resistance. And therefore, the steeper gradient will have the lower resistance. Okay. So the things you're going to sort of, and in the end, you're looking at, you're going to tell someone, first of all, that you know the gradient is 1 over R. You're going to know that it's Q, and you're going to somehow tell them that you know it must have a low resistance, and therefore the steeper gradient will have the lower resistance. So that's sort of, and knowing that your conductor must have a lower resistance. Does that make sense? Hopefully, all of you at this point, sorry, I'm going too quickly, have got some idea of being very careful when you're looking at Ohm's law. If it's V on the Y and X and I on the X, that's a win, because it means I can just go with V over I. But if it is I versus V, then it means I have to consider the fact that my gradient is 1 over R. Okay, so there we go. Okay, so what we're going to look at now is some circuits and some of what are known as your circuit rules. So remember, we talk about a series circuit. That's where things are connected one after the other. And then we have a parallel circuit where you've got components where the charges have to sort of split in order to go either down one path or the other. So when we're looking, and I'm going to use the notes, just then you can see where it is that this is in your summary notes. So this that I've got here and I've zoomed in on is from your summary notes. So it's not something that you have to try and quickly scribble to write down. So we're going to start off with the first one, which involves current. So when we have a series circuit, if I look at a series circuit, the current through all the components in the circuit is the same. So the rule that we have is that the total current is equal to I1, and I1 in this example would be what's going through ammeter A1. Oh, sorry, that was supposed to be I1, not IA. I1, and that would be the same as I2. So the current through both those resistors is the same. And in fact, if we had another ammeter here in the middle, let's say that was I3, that would read exactly the same value. So when we're looking and they're talking about IT, IT is essentially your total current in your circuit. In a series circuit is equal at all the points. And now, as we're sort of leaning towards getting to internal resistance, to remember that that is the current that's also passing through your battery or your cell. Now, when we get to parallel, so here we have a parallel circuit, I'm going to put another ammeter here, and I'm going to say this ammeter is going to measure AT. Okay, so what we're looking at here in a parallel circuit is that the current splits. And in fact, we say that a parallel circuit is a current divider. So a parallel circuit divides current. Okay, so when I look at this total current, which is sort of in the series part of my circuit, that is equal to the current through the one branch plus the current through the other branch. So this would be I1, and then this would be my I2. So once I've done the whole thing about potential difference, we're going to talk about how it divides. Okay, how do we know how much current goes in each branch? So please, here, this is now a combination of series and parallel. So as it stands here, R1 and R2 are in series. These two are in series. So exactly the same current flows through R1 and R2, and that would be the current I1. Okay, so current I1 flows through those two. If I look here at current that's flowing through R3, which is I2, that then only flows through R3. And then again, my total current in my circuit is going to be made up of A1 plus A2. So R1 and R2 are in series, but they are in parallel with R3. So if I look at potential difference, and I look at the rules for potential difference, then again, we come to a series. Sorry, I've gone here. Here, I'm going to come to the rules now for resistance. If I look at a series circuit and potential difference, now we're in series, and in fact, a series circuit is known as a potential divider because it actually divides potential difference. So if I look here, and this, let's say, was my VS, which is S for series, that means that VS is going to be V1 plus V2. Okay, so it actually divides the potential difference between the two resistors. And again, I'm going to look at how it divides. Now, the one that causes a lot of confusion with children and with students and young adults, sorry, is parallel. Now, when I look at a parallel branch, what you have to realize in a parallel branch is that the potential difference across each branch is the same. So the potential difference is the same, but remember the current divided. And exactly the same if I'm in series, the potential difference divides, but the current was the same. But if I look at this parallel circuit, V1, which is across the top branch, is going to be the same as V2, is going to be the same as across the whole branch. And that is because charged particles, remember, are moving in my circuit. And they either are going to go through their R1 or they're going to go through R2. They are not going to go through R1 and R2. Charged particles will go through one or the other. And when they go through one or the other, they are going to transfer their energy. And because of the fact that both of them, if I look at where I start at the parallel branch and where I end, the charged particles come together to the same point, which means everything at that point is at the same potential. And that is why they're going to transfer the same amount of energy. How do they do that? Because the currents are not the same. So remember, the V's are the same, but the currents are not the same, and the R's might not be the same. And then if we look at this last one, which is a combination of series and parallel, it means that again, R1 and R2, remember, are in series, so that they are potential dividers. But if I look at R3, that is in parallel with that whole branch. So it means that V3 must be equal to V4 because of the fact that that's the full potential difference across that branch. But V3 or V4 would be equal to V1 plus V2 because it is going to divide. So these laws about current and potential allow us to come up with our formulas for calculating resistance in series and calculating resistance in parallel. So let's go and do some examples. So if
Sorry,
we
ma'am.
look, yes,
Ma'am, where does the voltage divider formula and current divider formula fit in there?
where do they?
I'm asking the voltage divider formula and the current divider formula, where does that fit in there?
In the, you mean where does it sit in the?
Like I'm asking, where does it sit in terms of voltage and current, the two different formulas for voltage and current in series and parallel?
So are you asking, no, so I think I'm struggling a little bit understanding what, so where, you mean where, which one do you use at which time?
Yes, ma'am.
Okay, so that I'm going to show you now with actual values. I think maybe, and then you can let me know if you're still a little bit unsure about what we're doing. So if I look,
sorry, Diane, I'd actually like to jump in. Could we draw 3 resistors underneath each other?
in parallel, or just 3?
So we're going to connect them in parallel. Let's make the first resistor 1 ohm, second resistor 100, and the third 1000. Okay, guys, so something super important to realize about this arrangement, and I know a lot of teachers have different analogies to explain this, but if you think about this pathway, let's say for argument's sake, we have a current node entering on the left, so your charges can enter this grid on the left and exit on the right. Do you agree that 1 ohm is significantly less than 1000 ohms? So let's imagine this. You're in a queue at your local Woolworths or Checkers or ShopRite, and there's only one teller, one cashier that's open, and the entire queue of people have to go through that one cashier. Let's imagine that's your 100 ohm cashier. So that person is quite productive. They're checking everyone through, you're paying for your groceries, and you're leaving the shop. But this queue is getting longer and longer, and the manager realizes, okay, we need to add another cashier. So no one's on the floor, no one's available. So the manager says, okay, you know what? They're going to open another till and they're going to start helping people to get through. But the manager isn't used to doing this work. So let's imagine that the manager behind the till is like the 1000 ohm resistor. They're okay at allowing people to go through, but they're offering a lot of resistance to the process. So your manager is now allowing some people in that queue to go through their till, but they're a lot slower than the normal cashier. A lot slower because there's a lot more resistance to the process. Now they realize, okay, we have a crisis. This queue of people is going right into the shop. We need to make a plan. So they get an artificial intelligence robot to go sit behind a cash register. That's like your 1 ohm. And people just pretty much walk through. Everything gets tallied, taken off their credit cards. They just walk out with their groceries. So when you have multiple pathways for your current or the people to go to the cashiers, you agree that by the end of it all, they're going to exit the shop a lot faster as soon as you have multiple pathways. So if you just had your 100 ohm resistance and all the current had to flow through it, and then you add any other resistor, if you have multiple pathways for your current, the resulting resistance, listen carefully, the resulting resistance, if you have multiple resistances in parallel, the resulting resistance is always smaller than your smallest value. Let's look at it mathematically.
Yeah, I was going to say, yeah, because you preempting
So-
my next
so
thing. Yeah.
It sounds confusing, but let's
Yeah.
look at it mathematically. So let's say 1 over RT.
So let's do that one first. So the total resistance is 2. So if I do this, just to show, if I do that, then looking at our formula, which remember your 1 over RP is 1 over R1 plus 1 over R2. So in this example would be 1 over 2 plus 1 over 2, which would be 1 over 1. And therefore RP is 1. So here your total resistance is 1. So it means that, as James was saying, you've added more, your resistance is getting less. But what if I had a 2 ohm and a 1 ohm? I'm just choosing little numbers just because it's easier. So if I go and say, okay, now I've got a 2 ohm and a 1 ohm, I now go and work out my total resistance here. It's going to be 1 over 2 plus 1 over 1, which is going to be, it's going to be 1 over 2 plus 2 over 2, which is going to be 3 over 2, which means that my total resistance is then going to be, remember, you need to flip it over afterwards, 2 over 3, which is 0.67 ohms. So can you see that your first one, you only had 1, your resistance was 2. You added a second resistor of 2 and you ended up with a resistance of 1. And now when I add 2 and 1 ohm, my resistance is 0.67. It's always smaller than the smallest. So if we take James's example, which is a little bit more mathematics in my head, if we take James's example and we go 1 over 1 plus 1 over 100 plus 1 over 1,000, then that's going to be 1, sorry.
Help us in the chat, guys.
Yeah,
So
it's faster than me.
0.01. So it's 1,011.
So it's, yeah, so it's going to be 1,011, but that's 1 over RP. So therefore RP you must remember, you've always got to flip it afterwards when you do parallel. And that's then going to be, I'm just going to give you lots of decimal places just so that you can see it is actually still less than 1. It's 0.989. So his smallest resistor in his example was 1 ohm, and the total resistance is still smaller than 1, which is 0.989.
So in terms of Storm's question, Storm, you might have learned series and parallel equations that your schools taught you to memorize. Would you like to just share the exact formulas you're talking about? I think that you're speaking about voltage divider, for example.
Yes, so I am.
So what formula did your school teach you?
So for potential difference for voltage in series, they said if you cannot calculate the voltage, you can plug it into a voltage divider formula, which says V2 ohms is equal to R2 ohms over R total times by V total.
Oh, okay. Okay, now I understand what you
It's
asked.
a manipulation of the formula. Diane,
Yeah.
I don't want to confuse the rest of the students. So Storm, if you don't mind, let's discuss that in the break. It's just a manipulation of Ohm's law and the
Yeah.
voltage divider formula.
So what I wanted to get to here is, and which I was going to explain to Storm as well, is that if you look at, because I was actually going to get to how we get to 1 over RP is 1 over R1. If we look at a circuit, for example, and what if I take, let's say this is 2 amps, and I've got a 2 ohm resistor here, and I've got a 4 ohm resistor here. So I'm going to start off with I'm going to make that R1 and I'm going to make that R2. And I'm going to say, okay, let's make this an 8-volt battery. Okay, so if I look at this circuit, pretty much I know everything about the circuit. Someone's told me the total V, someone's told me the current in series, and I only have to worry about series. And someone's told me my 2 resistances. But now if I wanted to look at V1 and V2, let's say here are my V1 and my V2, then what we're looking at, so I'm going to work it both ways. I'm going to say, if I was given that information and I wanted to calculate V1 and V2, very simply, I can apply Ohm's law. And if I apply Ohm's law, I can say, okay, on your data sheet, R is V over I. So it means that V is then I times R. Okay, so if I look at V1, V1 is going to be 2 amps is flowing through the 2R resistor. So V1 is going to be 2 times 2 is going to be 4 volts. If I look at V2 then, V2 is going to be 2 amps times the 4 ohm resistor is going to be 8 volts. So you'll see V1, 4 volts, V2 is 8 volts. So if I look at these two, V1 and V2 are 4 volts to 8 volts. And R1 to R2 are also in a ratio. So when we talk about what's happening in series, is that we need to share, in fact, it can't be 8. I've done something wrong here. That can't be 8. I know what I've done wrong. Sorry. I'm going to go back. I've just realized that this is what happens when you give kids, you give everything. This, sorry, would have to be 4 plus 8 is 12 volts. Sorry, apologies. So if I look at this circuit, what is happening is that there's 12 volts available. Now you need to start seeing potential difference as energy, essentially. That there's 12 volts, and I'm not going to, it's joules per coulomb, but I'm not going to every time say joules per coulomb. There's 12 volts available. That has got to be shared to the circuit. So when these charge carriers move through the circuit, what they are doing is they are transferring energy. Now, if we look at wires and we make the assumption that our wires have negligible resistance, that means they are not transferring any energy in the wires. So if I look at everything that I've done at the moment that is yellow, and I had to put a voltmeter from yellow to yellow, anywhere on that yellow line, those 2 points on my circuit are at exactly the same potential. And because they're at the same potential, there is 0 potential difference. So that voltmeter is going to read 0 volts because there's no difference. But if the charges now go through the 4 ohm resistor, what is the 4 ohm resistor doing? The 4 ohm resistor is giving opposition to the movement of these charges. To push those charges through that resistor, those charges are going to transfer energy. It's going to transform from to maybe some heat. If it was a lamp, it would be to light, but there is going to be a transfer of energy. And what that means is that the amount of energy the charges have after they've pushed their way through that R2 is going to be different from when they entered. So if I'm going from right to left, then the energy is going to be less. So that means that V2 is reading the difference in energy between green and yellow, and which means it's reading the difference in energy of the amount of work that was done to push these charges through that little resistor. So if then the charges now, they've gone through R2, they are now going to go through R1 and give away their energy. So if I look now at the V1 is reading the potential difference across pink and green. So if I go back to my original battery, my battery provided energy, and we said it was 12 volts. Eventually I got it right. 12 volts, which was between a potential of 12 and a potential of one side of pink, sorry, and the other side of yellow. If I look at the rest of my circuit, any charged particle gave away and went from yellow to green, and that was 8 volts, and then from green to pink, and that was 4 volts, which means in total, the charges gave energy away of 8 plus the 4, which then takes me back to my 12. So when the charged particles move in series, they are going to, that would be like, you've got James' analogy of going through a till. It would be like you'd have to go through one and another, which means that in that instance, you are going to have to do some with the one. Let's say the one till only does vegetables and the next till does meat. You would go through the first till and then you would go through the second till. And therefore, in total, the amount of time, the amount of energy that's been dissipated is the sum of those two, or the amount of groceries that you managed to bring through the till. But when you're in parallel, you essentially only have to go as a charged particle or as a person going through a till, as in James's example, you've only got to go through one or the other. And because you're only going through one or the other, depending on, as James was saying, the 1 ohm is someone who can let people go through quickly. If that is going faster, then that means in that 1 ohm resistor, if the particles can go faster through, that means that the current is going to be bigger. Then, let's say with 100 is somewhere in the middle, then the 1000 ohm where the current is going to be lower. So when you have a parallel branch, to show you here, if I have parallel branches, let me just, and let's say, again, let's make this 1 ohm and then make this, I'm just going to make it easy because then I can maybe work out 2 ohms. As it stands here, the charged particles, I'm just going to again work this, the charged particles are not transferring any energy. So let's say a charged particle goes through the 1 ohm, transfers energy, so there's a potential difference across the 1 ohm. Once it leaves the 1 ohm, it goes back to the battery. Why doesn't it now go backwards to the 2 ohm? Because remember, you've got to keep in the back of your mind that your battery has a positive and a negative potential. Okay, it's like an electric field. If you've done, remember your electrostatics. Casey, you're dealing with conventional current. Actually, that is conventional current that goes from positive to negative. But actually charges are flowing from negative to positive. But yes, you're right, conventional current. Sorry if I've taken a while to answer you, Natalie. Conventional current is from positive to negative. But in the end, remember, it doesn't matter whether you're going from clockwise or anti-clockwise. In the end, the charged particles are always starting and ending. So when you get to sort of slightly more advanced or sort of people are trying to go from first principles, sometimes they say, okay, let's pretend the positive is at 12 volts, let's make it 12. and then this is at 0 volts. That means the difference in my battery is 12. And as long as I'm still going, if I'm going clockwise or anti-clockwise, in the end, it doesn't matter because the difference is still a value of 12. And if you go clockwise, you may be looking at negative 12, and that would be how you connect your actual voltmeter to your circuit. But in the end, a charged particle is either going to give away its energy to the 1 ohm and go back, or another charged particle coming along here, it's going to go there, but now it also is going to give its energy away. But now, if I look, the pink and the yellow are all exactly the same line. I've gone through nothing, which means that instead of saying, okay, I'm going to make that pink, this is also all yellow. All of these are at the same potential in terms of no potential difference has been given away because there's no resistance in the wire, which means that if I go and look at the other side, surely then all of this must be at exactly the same potential as well, because of the fact that it links to the battery again, which if I now put a voltmeter here, let's say that's V1, and I put a voltmeter here, it means that those are at the same potential difference, but it doesn't mean the currents are the same. So if you can just keep in your mind that with James's analogy, that he spoke about the resistance, which was the actual resistance value, and the number of people who can go through, and that is the current. What we are looking at here is R times I, which is going to be equal to V. And in parallel, the V's are the same because of the fact that once things have gone through, they are going to be at the same potential on either side. So what that means in a parallel circuit is that if I look through the 1 ohm resistor, the current to be able to get to the same, so V1 must be equal to V2. So this store maybe is a sort of where you're looking. That means that the current through resistor 1 times resistor 1, so we're going to make that R1, we're going to make it I1, we're going to make this I2 and R2, must be equal to I2 times R2, which means that I1 over I2, if you want to think of a ratio, is R2 over R1. So essentially, what is that saying? That when we're in parallel, the smaller resistor, which is the 1 ohm, has got to get the bigger current because I times R must be the same V in both branches. So if you had just an example here, back to James's analogy, here, if I had an ammeter here, let's say this ammeter read 1 amp, okay, then it means that the V in the circuit would have been 1000 ohms times 1 amp. The V here would have been 1000 volts. It means the V here needs to be 1000 volts and 1000 volts. So to get 1000 volts through this 1 ohm, if it's a 1 ohm, and remember, V is I times R. If the 1, this is 1, what is I going to be if I need to end up with 1000? That means my current here is going to be 1000 amps. And here it's going to be 10 amps. 10 times 100 gives me 1000. 1000 times 1 gives me 1000. 1 times 1000. So just to do a cleaner version of that. So what James was showing you is that you've got a 1 ohm, you're going to have 1000 amps. In your 100 ohm, you're only going to have 10 amps. And in finally your 1000 ohms, sorry, you're going to have 1 amp. So, but each of those will have exactly the same V. And that's why you've got to remember that the V's are the same. That is the fundamental overriding principle in parallel, is that the V's must stay the same. So if you're looking at so I just want to do this quickly so I can go back up again. If you're looking at your series, again, if I give you a circuit and I say, this is 1 ohm, and this is 2 ohms, we've gone very far over, sorry. And if you know that this is 6 volts, and you've got to work out these V's, V1 and V2, you know that 6 must be equal to V1 plus V2. And if you know that 6 must be equal to V1 and V2, because V1 and V2 are crossed to series, that means that these two must be splitting, that 6 must be splitting, and it does not split in any strange ratio. It actually splits in exactly the ratio of the resistances. So if I've got 1 ohm ratio to 2 ohms, it means that my volts are going to be in exactly the ratio of 1:2. So this is my resistance ratio. My voltage ratio is also going to be 1:2. So if you had to calculate what is V1 and V2, you would say, okay, hopefully your guys' maths, I'm sure you're all good at your maths core. The one way of doing it is you can work with ratios, and you could say that this is going to get 1 of, what's the total of my ratio is 3, because it's 1 plus 2. This is going to get 1/3 of the total. Okay. And this one is going to get 2/3 of the total. So it means this one is going to get 6/3 is 2 volts. And this one will get 4 volts. Okay, so that then would be 2:4. But can you see again, it's still in the ratio of 1:2. So I don't know if a lot of you might have learned the working out the ratios of your V's, and it's the same as the ratio of your currents, but current ratios I know can be very confusing, and sometimes it's easier to rather work with numbers and questions. So let's go to a question. So I want to go to question, let's just go to 7.4b. Okay, so let's do a question so that we at least, before we come back, so this will be 6.4b, or this will be 7.4b. Okay, in the following circuit diagram, the internal resistance of the ammeter and the 6-volt battery is negligible, so we're not going to worry about internal resistance. The voltmeter has a very high resistance. That means we can ignore it. It means that our meters are doing what they're supposed to do. So they've told me the total V. If I look at the circuit and the information I'm given, you'll notice you told the voltage for the battery, so it means you know your total volts. When you look at your circuit, you'll see that you do know every single resistor in the circuit. Okay, so now, when we're looking at the first question, they're asking us to find equivalent resistance. Okay, so I'm going to come back to what is this word equivalent of the parallel network. So I'm going to ask everyone to take out your calculators, and you're going to do for me, you're going to give me an answer. So we've got a 4 ohm and a 12 ohm. You guys go and work out for me, what is the equivalent or total resistance of this parallel branch? Okay. So let's give you a minute. Here we go. Okay. Okay, so I just quickly want to go. So it would be 1 over RP. Remember, is 1 over, this is on your data sheet, 1 over R1 plus 1 over R2. So it's going to be 1 over 4 plus 1 over 12. So if you put that into your calculator, it's going to come as 1 over 3. Okay, and therefore be careful. Then that means that therefore RP is 3 over 1, which is then 3 ohms. Now, what you've got to be careful with, I just wanted to go back to Amar, is I think you might have thought that the other 3 ohm was also in parallel. Be very careful. If you look here, I'm just going to quickly use a highlighter to show you. Can you see that 3 ohm is in series? and only the 4 ohm and the 12 ohm are in parallel. So I'm assuming that that's how you got to the 1.71. And they're deliberately trying to make you think that because of how they've drawn it. So what I always say to kids is take your finger. So let's pretend my mouth, or let's make my highlighter my finger. I always say to them, if you want to decide if something is series or parallel, start. So let's do conventional current so that I don't confuse you for the electromagnetism. I say, take your finger and move through. If you don't have to pick up your pen or make a choice, it means you are in series. So everything I've done in green there is in series. And then I have to now make a choice. I'm either going to go through the 4 ohm and back to the battery, or I'm going to go through the 12 ohm and back to the battery, which means that the 4 and the 12 are actually in parallel. Okay. So it means that they now want you to find the reading on the ammeter. Oh yes, I did want to just talk about this word equivalent. What does that mean? So what I wanted to just show you was that it means the following. I could have done this 6 volt, 3 ohm that was there already. I could have replaced both of those with one single 3 ohm resistor, and it would have had the same effect in my circuit. So instead of this parallel branch, I could have put one 3 ohm resistor, and I would have had the same current in my circuit and the same voltmeter reading. Okay, so that's what it means by equivalent. So calculate the reading on the ammeter. Now to do the reading on the ammeter, I'm going to have to calculate my total current. So my total current means I need my total resistance. So if I know this part is 3, quick, let's see if your fingers are fast. What is my total current going to be? Okay, Storm's gone all the way. Nakia, thanks to you. 1 amp, people are going much faster than me, so it'll be good. I'm getting lots of 1 amps, well done. So my total would have been 3 plus 3 is 6 ohms, and therefore I'm going to go and apply Ohm's law. I is V over R, which is 6 over 6 is 1 amp. Well done, everybody. Okay, so that means that reads 1 amp. They're then asking for the reading on the voltmeter. There are a whole lot of different ways of doing this. I'm going to just do quickly to do 2 ways, just because sometimes you get stuck and you worry because you can't do the one simple way and you don't know how else to do it. If I had placed a voltmeter here, I'm going to make it V1. Remember that that 1 amp is in the series part of the circuit. It means that that 1 amp is also flowing through my 3 ohm resistor. So that voltmeter there would read I times R. Remember, V is I times R, would be 1 times 3 would be 3 volts. And then I can say, okay, I know that there's 6 volts in total in my circuit. So that means if this has got 3 volts, it means I'm going to know that that has got to be 3 volts. Okay, lots of, I'm great. Glad to see so many people got the right answer for the current. Well done. So that's one way of finding the reading on the voltmeter. The second way is you could go and say, well, I know that this here, all of this is the same as 3 ohms. So again, you could have said, no, what I'm going to do is I'm going to go V is I times R for this side. And I know the total current of 1 amp will go through the total resistance of that branch, which is 3, which will give me 3 volts. And lastly, I'll do a quick thing about breaking current up, but it just becomes very complicated, and it's always easier to work with volts to get to current than to try and do ratios with current. And I don't want to get too bogged down in ratios. But they're asking you now to find the current. Let me just get rid of all my things here. They want you to find the current in the 4 ohm resistor, question 1V. Okay, so if I know this is 3 volts, it means the quickest way, grade 11s, to find current in a parallel branch is to take the V across the branch and divide it by the resistance. So for that one, if I want to work out, I can go I is 3. How do I know it's 3 across the 4 ohm? Because remember, they're in parallel, so the V's are the same. So it means that I is going to be V over R, which is going to be 3 over 4. Well done, Benati, is 0.75 amps. Storm, be careful, you've done the 12 ohm. Yeah, because remember the 12 ohm will have the bigger, so if you've worked out the 12 ohm, then subtract that from 1, and then you will get to the, Storm, did you use ratios there?
No, ma'am, I calculated the 12 ohm.
Okay, no, just checking, yeah. Because sometimes kids use ratios and they don't realize that when we're talking about current, remember the bigger current must go through the smaller resistor. So you've always got to swap. If if you found it for the one, you must make sure you swap the ratios with current. Then it's just asking about the most energy transferred. Please, we have got, I'm just going to write here, the formulas we know, R is V over I. What we haven't spoken about is that you've also got a whole lot of work and energy formulas. You've got W is VIT, you've got W is V squared over RT, and you've got W is I squared RT. That's for work. And then for power, you've also got VI, you've got V squared over R, and you've got I squared R. So if they're asking which of them has the most energy per second, then essentially I've got to look at using a formula, either VIT, V squared over R, or I squared R, that's going to compare these two resistors. So I'm just going to go across here and I'm going to say, okay, I've got a 4 ohm resistor and I've got a 12 ohm resistor. I always suggest, grade 11s, that you choose a formula where something is the same. And what is the same for these two is the V. You don't have to, but it does make life easier. So if I go and use P is V squared over R, okay, why am I using P and not W? Because they're saying energy per second. So remember, energy per second, they're actually asking me about power. Just be very careful. If they say the most energy, it's not going to change your answer, but just be careful. They're actually wanting you to find power. So if I look at those two, they both had 3 volts across them. So if I look and I calculate for the 4 ohm, so I'm just going to write here P for the 4 ohm, would have been 3 squared over 4, and of the 12 ohm would have been 3 squared over 12, which means, sorry, I'm just going back. They were asked as the most, so the one that's going to be the most, therefore, will be the 4 ohm, is going to be greater than the power through the 12 ohm. You could have obviously, since you could have said, no, I don't like doing that. I want to use P as VI. But then you're going to have to realize for the 4 ohm, you knew the V was 3, you knew the I was 0.75. And if I look at the 12 ohm, you would have had to have then gone and said, you know, the V is 3, but you would have had to go and work out the I. So remember, you would have had to have said the current through the 12 ohm, just change it quickly. Remember, that would have been the 1, which was my total current, minus 0.75. And that's where I got the 0.25. And then again, if I look at this, you'll see very definitely, again, therefore, same logic, the power in the 4 ohm is greater than the power in the 12 ohm. Okay. But I always suggest with these questions that you start with the formula that's got something the same. Okay.
Quick question. Will they get the power and work formulae on their formula pages?
Yes, they get all of the ones that I've written there are all on the data sheet. Yeah, these are all on the data sheet. R is V over I, W is VIT, P is VI. Yeah.
Okay, let's do one more question and then we'll take a break.
Okay. So then let's look at another one that has got no internal resistance. In diagram 1, you've got two non-identical resistors, X and Y, are connected in parallel across a 6-volt battery. The current through A1 is found to be 2 amps. In diagram 2, they're connected in series, so which remember now means they're going to share the 6 volts. V2 reads 4 volts. The internal resistance can be ignored. So if I look at diagram 1, I think everything's in the picture, so it's all good. Diagram 1, who can tell me how much the potential difference is across the X? You can tell me what the potential difference is across X, or what is the potential difference across Y? Okay, good, Benati. Anyone else? Good, Lani. Yeah. Tabo, good. Storm, Amara, good. You all excellent electricians. Well done. Okay, so everyone very correctly is telling me it's 6. Why? Because if you look, there's nothing else in the circuit. So it means that the potential difference across, sorry, I'm not in my drawing tool, the potential difference across X is going to be 6 volts and across Y is going to be 6 volts. Okay, is there anyone who's not sure why it's 6? Everyone okay? If you're not, just maybe put a hands up, and then I can know that I must just look at it again and go through again why it's 6. Okay. Then if I look at this, they asked me to state Ohm's law. So they're obviously trying to give me a hint and saying to me, you must be using some version of Ohm's law. So remember, that is that the current through a conductor is directly proportional to the potential difference across a conductor at constant temperature. So now if I look at, they want me to calculate the resistance of X and Y. Now, if I look at my circuit, where do I know the most? In circuit 1, in diagram 1. I know the most about resistor Y. I've got the V and I've got the I, so it means I can find the resistance of Y. So let's go and see the resistance of Y. I'm going to use V over I, and that's going to be my 6 over my 2, which means the resistance of Y is going to be 3 ohms. So it means I know Y is 3 ohms, which means I can go and put into my second circuit that Y is 3 ohms. Okay, because it's the same, even though they're in different circuits, it's the same resistor. So now, unfortunately, there's nothing more I can do in diagram 1. I don't have enough information to carry on with diagram 1. So now let's go across to diagram 2. Who's going to tell me what is the potential difference across Y in the second circuit? Good, quick fingers here. Well done. Anyone who hasn't answered, Benati, Lichle, good. Nice to see some newer names giving me some answers. Good, Mara. Wonderful. You're all very brilliant. As I said, 2 volts. Okay, why is it 2 volts? Remember, they're in series, so they must share. So the 6 volts must go. If there's 4 already for X, it means that there must be 2 volts left for Y. So now there are 2 ways of doing this. The next question, which is to find the resistance of X. The long way around, okay, if you don't like ratios, the long way around, so I'm just going to keep this here, and I'm going to just get rid of this so that I don't want to go away from the picture. The long way around is to work out the current. Because again, what can I do? I can calculate the current in my circuit. So if I work out the current through Y, that will be V over R. So that's going to be 2 over 3, which is then 0.67 amps. but the current through Y is the same as the current through X. Why? Because they are in series. And then lastly, I can say therefore the resistance of X is going to be V over I, and that's going to be 4 over 0.67. So if I don't do a rounding answer, I think that comes to 6. Let me just, it's going to be 4 over 2 over 3. And yes, so if you don't use a rounded answer, you get 6 ohms. If you do, I think you get 5,89 if you use the 0.67. 4 over 0.67, 5.97, sorry. So that then comes to 5.97, yeah. But for me, I always say to kids, if you're not going to, if that's not a final answer, rather keep the value in your calculator so that you're not using a rounding and a rounding and a rounding. And what some schools do suggest is that if this, I'm just going to come back to this one, if this is your in-between answer, how you can sort of get away with not really worrying about holding it in your calculator is some schools sort of say, we'll keep at least 4 decimal places, and then you should be fine. So let's see if we do that. If I go 4, 0.6667, then yes, I get 6 ohms. So that's one way of trying to make sure that you don't have to worry about holding something in your calculator, is if you keep at least 4 decimal places in between. The other way of doing it, the quicker way, is ratios. Okay, how do I work with ratios? Is if this is 4:2, because remember this is 4 volts and this is 2 volts, that means that if this is 3 ohms, because I'm in series, my resistors must be in the same ratio, which means this has to be 6 ohms. So that it is, because it's double the volts across the X, therefore it must be double the resistance. So that would be the quick way of getting the answer. Okay, so what I'm going to do is I'm going to, through the question 7.1b, we're going to go through an example of where there is this internal resistance. So as James was mentioning this concept of internal resistance, when you do chemistry next year in grade 12, you're going to do a section known as electrochemistry, and you are going to learn about how to make a battery from chemicals. And those batteries, the nature of the way that they work and they create electricity, there is resistance in the actual battery itself, which yes, can cause a problem. It can have 2 problems. Number one, it can mean that the battery gets very hot. And secondly, it means that it might not be delivering the same amount of energy to the circuit, which is what its purpose is, as you require. So the first thing we just need to quickly touch on is that when we're looking now at a battery or a cell, we now use the concept of internal resistance is shown. Those of you, I'm just doing this especially for those of you who have not used this at all, haven't done anything about internal resistance. So this is essentially my battery or my cell. And if I look at this resistance now, I now distinguish between resistance inside my battery, which is a lowercase r. So R is internal resistance, and capital R, which on the DBE, you've got REXT in your formula. On the IEB, it's just R. That is your external resistance, or the resistance on the outside. So it's the resistance you've worried about all along. The next thing you've got to be aware of is that R and R are connected in series. So your internal resistance in your cell is in series with the rest of your circuit. So what is it doing? It's increasing the resistance in my circuit. So it means now my total resistance in my circuit is actually going to be the outside plus the inside. So that's for the IEB, it will just be R plus R. For the DBE, you've got REXT plus R, is basically what you're looking at is your total resistance. So that's the first thing to understand. The second thing is what are the words that we use now that are different from the other circuit. If I take the circuit as I've drawn it here, if I open the switch and there is no current flowing, okay, so they're not pushing charges through the battery, then that voltmeter across the battery is reading something known as the EMF. Very simply, for this very quick story, that is almost like the total volts that are available. It's like the total energy that the cell can supply to the circuit. Does it supply that when there's internal resistance? No. But when there's no current flowing, that voltmeter will read what is known as the EMF. The EMF stands for electromotive force, and essentially it is a voltage, and it is like the total volts available to the inside and the outside. It's available to the whole circuit. When the switch is closed, so there is now current, that voltmeter now reads something known as either potential difference. We now talk about it, it can be called potential difference. On the IB, we call it V load. Okay, and that is going to be less than the EMF. Okay, so what that means is that in my circuit, I've now got the EMF, I've got this V load, and now what is left, because the EMF is like the total volts, the V load is what is actually going on the outside. So this is what's going on the external to the outside. And what do I call the bit that's left? Because these two don't add up to each other anymore. And it depends on the different departments, but on the IEB, because this one is actually on your data sheet, it's known as V internal resistance. And the colloquial one is, we call it our lost volts. So what that means is that when we now have this internal resistance, not all of the EMF is actually going to my circuit. Only the V load part, only this section that's not being used up. So essentially, for example, just to give you an example, in this example here, they say in the diagram below, a battery with an EMF of 6 volts. So what they have told me is the total energy available for both the inside resistors and the outside resistors. And that is my EMF. They're telling me this battery has an internal, it's V. So Letabo V internal resistance is the same thing. So what I'm going to show you now is that you get these formulas. So unfortunately for you guys on the DBE, you only get one formula, and it looks like this. It's EMF is I REXT plus R, which I'm going to very quickly show you how you get it. What's nice on the IEB is that we get 2 formulas. So you get that one, and they very kindly tell you the relationship between that formula and the lost volts and the V load. So this is what you get on the IEB. So these two are the IEB formulas, and then this one. So this is the DBE, and then this is the IEB. And I know it looks like someone's introducing a whole new formula. So I really just, especially for those of you that are new and have never seen this, I just want to quickly show you. Remember, EMF is total volts. I need you to remember that. In my circuit now, my total resistance, remember we said, is what's on the outside and what's on the inside. So let's go and look at Ohm's law. What does Ohm's law tell me? Ohm's law tells me that I is V over R. So if I now look at my total current, which is my series current, which is what is going through both the inside and the outside. If I go and work with total volts and total resistance, I've got a new word now for total volts. It's EMF. My total resistance is both inside and outside. And can you see that actually what I've ended up with is this formula I wrote on the right-hand side here. I've basically taken my current and times it by R plus R. And this is where this formula comes from. So I know a lot of you think, oh, this is some new formula. I need to think it's some different relationship. It's not. It actually is a version of Ohm's law. All I'm doing is I'm bringing in EMF and total resistance. So let's look at an example on what they want you to do. So firstly, if I look at this circuit, what do I have? So I always say to kids, if it's an EMF question and there's internal resistance, go and write down this. Okay, and let's go and see what I know. So what have they given me? They've told me the EMF is 6 volts, so I know that's 6. I don't have my current, so I don't have that. Do I have my resistance on the outside? I don't have a value, but I can calculate that. That is, I can calculate. How do I know I can calculate it? Because I've been given all of the R's. I know the 10, the 15, and the 10. Do I know my internal resistance? Yes, I do. So if you look here, I'm just going to write the I there. If I go and calculate my external resistance, my total external, I'm actually going to be able to find my current. So very often kids look at questions like this and they think, I don't even know where to start. Go and start with a formula that's for internal resistance, which is this EMF one. Look at what you are given in your circuit and go and try and put that together. So if I go here, let's go and calculate our resistance. So we're going to be very quick. We're going to do first the parallel, and then we're going to add the series. So I'm just going to go very quickly because we're trying to catch up. 1 over 10 plus 1 over 15. And therefore, if anyone can be faster than me, please feel free to drop me a, because you guys are definitely quicker on your calculators than me. Okay. So that's 1 over 6, and therefore RP is 6 ohms. So that means that my total external resistance, I'm just going to write here external, is then going to be 6 plus 10. Because remember, this is in series Q, is going to be 16 ohms. Okay, so if I come now and I want to calculate my current, I'm going to go EMF, you would write the formula, is IR plus R. So 6 is I 16. Remember, that's everything on the outside plus my 2 on the inside. And therefore, I is going to be 6 over 18, which is then that's a third. So that's going to be 0.33 amps. Okay, don't forget, Filani, you must turn it around. Well done that you got the 1 over 6. I think you were telling me what the answer was for my 1 over RP. Thank you.
Guys, quick one. Let's just consider what the current would have been if you didn't have an internal resistance. You should be able to type it in the chat for me. If you did not have an internal resistance, what would your current have been? Ohm's law.
Wait, ma'am, can you please just go a little bit up so I can just see the
oh, all good. Oh, I'm in the chat. My mouse is sitting over the chat. Give me a sec, sorry. Why are you not doing anything? Sorry, just give me a second. And what's going on here? Anyone else? Okay, anyone else got an answer for us? What would our total, I think it was it Storm, or who was asking, Chris or Storm? Can you see now it's 6 volts is the total? Anyone else got an answer? Well done, well done. Lots of correct answers here, good. Leclerc, you remember you would go, oh, I know what you've done, Leclerc. You've gone you're looking at the EMF and the internal resistance. Remember that if there had been no internal resistance, it's like that doesn't exist. It's like I can cross that out, which means it's in the circuit. It means I would have gone, if we're going straight forward with Ohm's law, it would have been I is V over what R, which would have been 6 over, and the 16 on the outside wouldn't have changed. So that would have been 6 over 16, which would have then been remember, if I'm calculating my I, 6/16 is then you've either got 0.375, or as some of you have correctly rounded off, 0.38 amps.
So the conclusion from that is that when you don't have an internal resistance, or the lower your internal resistance, the more current can be supplied to the circuit. You guys all understand?
Is everyone okay with the fact that, as James was saying, if this wasn't there, the 2 ohms, you would get a much bigger current. If you compare before, we got 0.38 without internal resistance. Remember, we only got 0.33. Okay.